Now coming to the next part of the metallurgy, we will see a lingam diagram. Alright. Now we have studied that the oxides of metals are reduced to metallic form in number of ways. The concepts of thermodynamics are quite helpful in selecting the most suitable reducing agent and for the reduction of a particular metal oxide. We have studied in class 11. Now here we are going to study that it helps in predicting the optimum temperature at which the reduction gives the best result. Listen carefully again. Here we are going to study that it helps in predicting the optimum temperature at which the reduction will give you the best result. Means the yield of the metal will be the maximum when the reduction is going to take place in what you can say in the blast furnace, we can say. So according to thermodynamics, the feasibility of any chemical reaction or process is expressed in terms of Gibbs-Helmholtz equation. Alright, the feasibility of any particular process, it can be expressed by delta G naught. Got it? That is Gibbs-Helmholtz equation. Delta G naught is what? Delta G naught is delta H naught minus T delta S naught. Where delta G naught is standard Gibbs free energy, delta H naught is standard enthalpy change, T is the temperature in Kelvin, which is generally 298 K at room temperature, and delta S naught is the standard change in entropy. Got it? In order that a change or reaction may be thermodynamically feasible, listen carefully. Delta G naught must have a negative sign. You have studied in the lower classes in class 11 that delta G naught, if it's negative, then the reaction is spontaneous, feasible. If it is positive, it is non-spontaneous or not feasible. If it is 0, then the reaction is in equilibrium. Got it? So when it is delta G naught is negative, what does it mean? That there must be decrease in free energy. In case delta G naught is positive, just now I said you, the change of the reaction will not take place. So always we must see that in a what you can say in a thermodynamic equation, that is delta G naught has to be negative. So a lingam diagram, you can see on the screen now, is a graph showing the temperature dependence of the stability for compounds. This analysis is used to evaluate the ease of reduction of metal oxides and sulfides. Alright, generally the ores are basically oxides and sulfides. Now it was constructed by Harold Ellingham in 1944. In metallurgy, it is used to predict the equilibrium temperature between a metal, its oxide and oxygen by extension. Reaction of metal with sulfur, nitrogen and other non-metals. We can say that. A reaction is said to be feasible, alright, when its del G is negative, just now I said you, and if del S is positive. Alright. So when T is increased, mind it, the value of T delta S is increased and it becomes greater than that of delta H. So when T delta S is greater than delta H, this makes the value of delta G negative and the reaction becomes feasible. So what is the condition? When T is increased, the value of T delta S is increased. Alright, and which makes greater than delta H, and when T delta S is greater than delta H, then delta G will be negative and the reaction will become feasible. Alright, if it is delta G is positive, the reaction is not feasible. Alright, that is what we come to know from the Ellingham diagram. Alright, we see that there are some coupling reaction is being taking place. It can be easily understood with the help of Gibbs free energy. Alright, when we draw a graph, delta G naught versus T, when we draw a graph, we can say that clear. So you can see the graph, you can see it here, delta G naught versus T, the graph it is being shown here. This is the Ellingham diagram. There is a graph, you can see that. So the graphical representation, it consists of plot of delta G naught versus T. Formation of oxides of element is nothing but known as the Ellingham diagram that I said you. And the important features of this Ellingham diagram is that you can see that now you can consult this particular diagram and you can understand what are the important features of this particular diagram, we can say. The first is that the curves for the formation of the metal oxide always slope upwards. You can see always it is going upward, all the curve we can say. That is for the non-metallic oxide only it comes downward, otherwise for all it is going upward, you can see that. That is slope upwards because delta G naught increases with the rise in temperature. In some curves, there is sudden change in the slope. Alright, for example, you can see zinc plus oxygen, zinc oxide. Then you can see magnesium plus oxygen, magnesium oxide. There's a sudden change in the slope in the curve, we can say that. Got it? This happens at the melting point or boiling point. You have studied in the lower classes also that when the change of state takes place, then the temperature becomes constant. Got it? The temperature does not show any rise, and hence there is a sudden change of slope, we can say that. So there is a large what you can say change in the magnitude of delta S naught, and that is it becomes highly negative. Got it? Consequently, delta G naught will become highly positive. Alright, again I repeat, in some curves there is a certain change in the slope. We can say I gave you in the figure, you can see in your screen, that is Mg, 2 Mg plus O2, 2 MgO, then zinc plus oxygen, zinc oxide, where it is taking place, this particular, the sudden changes. This happens at the melting point, at the boiling point temperatures of these oxides, where there is large change in the magnitude of delta S naught, and it becomes highly negative. That is, delta S naught becomes highly negative. If it is negative, then delta G naught becomes highly positive. For metals like silver and mercury, delta G naught exceeds 0, that is becomes positive at high temperature. This means both silver oxide and mercury oxide decompose of their own at high temperature and no reducing agents are required. Alright, so here for that reason in Ellingham diagram it is not there. That is, we come to know that 2Ag2O on heating will give you 4Ag plus O2. 2HgO on heating will give you 2Hg plus O2. Here no reducing agents is required, because on heating, what you find? On heating, metals like silver and mercury, the delta G naught exceeds 0, becomes positive at high temperatures. So when it is exceeding 0, that is both silver oxide and mercury oxide decompose of their own and we don't require any. Alright, when the value is exceeding 0, it becomes positive at higher temperature. What does it mean? It means that mercury oxide, silver oxide does not require any external energy. Means you don't require any external agent to reduce it, like carbon monoxide, hydrogen. You don't require it. Simply it will reduce. For that reason I said, 2Ag2O or 2HgO on heating will give you that is silver and mercury, and oxygen gas will be released. Now in the Ellingham diagram, the curve for the formation of CO shows a downward trend. You can see that 2C plus O2 gives 2CO. It shows a downward trend. This is quite expected because delta S naught tends to increase during the reaction, as is evident from the chemical equation. Therefore, delta G naught is likely to become more negative with the rise in temperature. Got it? So from the Ellingham diagram, it is evident that any metal oxide with lower value of delta G naught is more stable than the metal oxide with higher value of delta G naught. It's very simple, because if energy is the lowest, then only it will be stable. If energy is the highest, then definitely it will be less stable in nature. Alright, so moreover, a metal oxide placed lower in the diagram cannot be reduced by the metal involved in the formation of the oxide placed higher in the diagram. Alright, thus Al2O3 cannot be reduced by chromium. You can see in the diagram. That is, Al2O3 cannot be reduced by chromium. We cannot reduce it by chromium, Al2O3. Alright, why is it so? Because Al2O3 and chromium oxide, if you compare, then chromium oxide can be reduced by aluminium metal. The element or the metal involved in the formation of oxide placed lower in the diagram can reduce the oxide of the element placed higher in the diagram. Alright, listen once again. The element or the metal involved in the formation of oxide placed lower in the diagram, that is the diagram you can see there on your screen, can reduce the oxide of the element placed higher in the diagram. Alright, that is, silver oxide and mercury oxide placed at the top position are quite unstable and they decompose of their own for that particular reason. They decompose of their own, you can see that. Silver oxide and mercury oxide, they decompose of their own because due to this particular reason, you can see. So these are salient features of the Ellingham diagram. I have said you, and you can see it here. Chromic oxide is placed above and aluminum oxide is placed below. For that reason, aluminum oxide cannot be reduced by chromium. Hence, chromium oxide can be reduced by aluminum. Here, chromium oxide, you can see, which is placed above, and aluminum oxide, which is placed below, can be reduced by what you can say, aluminum metal, chromium oxide, we can say that. Thus, the relative tendencies of the different metals to undergo oxidation react as reducing agent is calcium is greater than magnesium, is greater than aluminium, is greater than chromium, is greater than iron, is greater than nickel, is greater than mercury, is greater than silver. So, magnesium metal is normally not used for the reduction of alumina, though it is quite feasible. Magnesium metal is not used. Alright, though it is quite feasible, we can say that. Clear. Now, though it is quite feasible thermodynamically, actually the point of intersection of the two curves in the Ellingham diagram, got it? The redox reaction is in a state of equilibrium. We can say that. The redox reaction. Here I am showing you aluminium and chromium. We can go back to aluminium and magnesium and we can show it to you. See here. See, we can see in the graph that magnesium metal is normally not used for reduction of aluminium. Got it? Now you see it here, magnesium. Why? Because the one which is lower, they can reduce. The one which is higher. Just now I said you. So the reaction can progress above this point, but at the temperature required would be so high that the process will not be economically viable and will also have some technical problems. You can see at the point A they are meeting. Alright, so what is that? Actually, the change in entropy will be higher when the metal formed is in the liquid state and in the solid state with reduction of metal oxide. So now what you find is that here, that is the delta G naught value is very high. Alright, the delta G naught value. In which case? That is in case of aluminium. Alright, magnesium is still higher. It's still higher. So hence, magnesium metal is normally never used for the reduction of alumina. We can say that. Alright, the graph should be lower. Alumina should be lower, and magnesium, if it is higher, then it can be used. But here it cannot be done. So the what are the limitations of the Ellingham diagram? What we do not know from the Ellingham diagram, the curves can interpret only the spontaneity of different reactions, whether feasible or not. However, they give no idea or clue about the kinetics of this reaction, that is whether the reaction is slow or fast. It does not say anything about it. This is the first limitations of the Ellingham diagram, we can say that. Alright, now next is, in all reactions that are considered, the reactants and products are presumed to be in the state of equilibrium. We are using the formula delta G naught is minus RT ln K. Alright, we are presuming it, we are assuming it that it is in equilibrium, and then we are doing it. Alright, so for that particular purpose, what you find is that the Ellingham diagram cannot say about the what you can say, the rate of the reactions. It cannot say whether it's fast, slow, or whatever it is. But what is the applications or the main usefulness of Ellingham diagram? The main application of Ellingham diagram is in the extractive metallurgy industry, that is known as pyrometallurgy. We can say that the process of converting the concentrated ore into metallic form upon strong heating, that is pyroheating to high temperature with a suitable substance, that is called pyrometallurgy. Again I repeat, the process of converting the concentrated ore into metallic form upon strong heating with a suitable substance, which is called as pyroheating to high temperature. Got it? So Ellingham diagram is quite useful to interpret the favorable conditions of temperature in the pyrometallurgy of the extraction of some metals like iron, copper, zinc from the respective ores. We can say that. Clear? From the respective ores we can come to know the Ellingham diagram. We can say that the Ellingham diagram, that is aluminum oxide is more stable than chromium oxide. Since the Gibbs free energy is negative, aluminum can reduce chromium oxide. Just now I've said you all these things about it, about this particular Ellingham diagram. I hope you understood. Now the one which you can see here on the screen, that is nothing but it's a bauxite. I have discussed with you how aluminium is extracted from bauxite. Just I'm showing you the picture of the bauxite ore. We can say that. You can see a very beautiful picture of the bauxite ore. You might have not seen earlier. Now this is a schematic diagram of the Bayer's process. I've discussed with you the Bayer's process. We are going to the crusher, then we are adding for the leaching process. We are adding NaOH, where it goes to digester, then it goes to the filter, then it goes to the precipitator. Alright, in this way it goes one by one. Got it? And finally we get aluminum hydroxide. From aluminum hydroxide it goes to calciner, and from there we get alumina. I've discussed with you that is all these things I've discussed earlier with you. Alright, so it is not a new thing, just I'm showing you the diagram because it is a schematic diagram. Earlier just I have told you about it, but this is schematic diagram. From the schematic diagram you can know that how the reaction process is being carried out in the Bayer's process. In the Bayer's process we have seen it, that is we are first going for the leaching, got it, of the ore we are going for. Then after that we are going for the digesting of the ore. Then after that we that is digestion, we get it nothing but the aluminum hydroxide as a precipitate, and from that we go for the calciner, and from there we get alumina Al2O3. So from bauxite we get, that is nothing but alumina, that is Al2O3, we are getting it. So that the Bayes process, we have read it also earlier. Just again and again I am saying you, just I am showing you this particular one so as to represent a schematic diagram, so that by the help of schematic diagram you will be able to understand it better, so to say. Got it? Now the next you can see is the extraction of aluminum. This I have also that is I've said you the Hall-Herold's process. You can see the diagram. For the diagram, the sake of the diagram I'm saying you, otherwise I've discussed with you about the Hall-Herold's process. In the Hall-Herold's process, what we are doing it, what is the use of the Hall-Herold's process. Here you can see the molten aluminum is collected. From there it is being collected in wooden vats. You can see the carbon lining which acts as a cathode, the carbon anodes. You can see the steel tank which consists of aluminum oxide dissolved in molten cryolite and phosphor, and this is the cell, the battery, you can see it there. Got it? So just to show you the diagram, that how it looks like, how the cell looks like, how the reduction process is being carried out, how electrometallurgy is being done. So for that reason I am showing you all these things. We can say that. Now this is all about. Thank you.